Hi, and welcome to this concept bite. Temperature is something we are all familiar with, and we will happily say things are hot or cold. Almost every day, I have at least one conversation about the temperature outside. But knowing that something is either hot or cold doesn't really explain what temperature is. To do this, I'm going to start with something I hope you are already familiar with, the Maxwell-Boltzmann distribution for the mean speed of particles in a gas. I've shown the plot with the probability distribution for low, mid, and high temperatures, and I have shared the equation for these lines, where you can see that there is a dependence on only the mass of the particle and the temperature. From this plot, you can see that the maximum probability moves to a higher speed with higher temperature. And hopefully, you have previously learnt that the root mean squared speed of the particle, one of the measures of average, depends upon the square root of the temperature. Therefore, there is a fundamental link between the speed of a particle and the temperature. Now, I'm going to bring you back to energy levels within molecules. All energy levels are quantized, with translational energy levels having the closest spacing. These levels are so close that it is difficult to observe this quantization except in very special circumstances. The faster a molecule moves, the higher the translational energy level it occupies. Here I show you the equation which shows the relative populations of energy levels. This relative population of energy levels depends upon delta E, the energy difference between the two levels, the relative degeneracies of each level, shown by G, and the temperature, T. Therefore, there is a fundamental link between the population of energy levels within a molecule, which is its speed, and so consequently, temperature is a measure of the average population of energy levels. If the degeneracy of energy levels is constant, the probability of finding a molecule in a particular energy level decreases exponentially as the energy increases. This is just what the Boltzmann distribution on the previous slide said. Just to note, you will learn more about degeneracy later in the course when you cover spectroscopy. If something has a high temperature, a large number of energy levels are populated, and the root mean squared speed will be higher. This is shown in the figure on the left. If the temperature is decreased, you can see the drop in the energy levels populated with this exponential probability. The mean speed is lower and the temperature, the average of the total energy in the different energy levels in the system, is lower. At very low temperatures, only translational levels are populated, but as the temperature increases and the energy is distributed over more levels, rotational levels are then populated, then finally vibrational. At room temperature, there is only a negligible probability of vibrational energy levels being populated. High enough temperatures would indicate that electronic levels could also be populated, but this would only happen at extremely high temperatures, significantly higher than we're usually concerned with in chemical reactions. Thinking about moving our temperature lower, or as we've come to think of it, the population of energy level, you can realise that if we follow this Boltzmann distribution, the ground translational state becomes ever more populated until T becomes 0. Then we can see all of the molecules are in the ground translational, rotational, and vibrational state, and there is no way the system can have less energy. This is the point where we would say the temperature is absolute 0 Kelvin. We cannot cool the sample to have a lower temperature. In fact, if we are thinking about rewriting the equation for the relative population of energy levels, replacing 1 over kBT with the term beta, then we can see the impossibility of cooling to absolute 0, because as T approaches 0, we are effectively trying to make beta become infinite. This term beta is recognised as a more credible description of temperature, but it hasn't found favour, and so although you may see it used in textbooks occasionally, the temperature T is the common term used in thermodynamics. So, just as I'm finishing, I'm just going to re-stress that temperature is a measure of the population of energy levels within a system. The more energy in the system, The higher the population of these translational, rotational, and vibrational energy levels, the higher the temperature of the system. I hope that this has helped to explain a concept we take for granted, but on a molecular level is often poorly understood. Thanks for listening, and if you have any questions, please do not hesitate to contact me.